Okay, I was asking this question, on which side will the eccentricity be? On 1, 2, 3, or 4? In this case, for this type of a question. So, Shreya, आप कह रहे थे 3 on,
Yes, sir, but not sure.
in quadrant 3. You're not sure?
Mm, yes, sir.
Now, anyone else?
Sir, sir, first,
I think it's first. Zakir. Now, what will it depend upon? You always have a load acting over a column. Now, this load is, if it's concentrically acting, for example, then that load would be, say, P load is acting over the column, and this is acting concentrically over a column. Now, in a case when you have the loads placed eccentrically, now that would arise when you have, for example, a situation like this. Now, in this case, there are loads acting on the slab, then onto the beam, and then those loads are going into the column. And you must have already studied this, that you then tend to get I'm just roughly drawing this moments in this fashion. For example, something like this. I'm not taking the sign conventions right now into account. So you will come to know, for example, if this column has got a fixed base, then there are end moments at the bottom of this column, and there is a moment at the top of this column. Now that moment M, now how did this moment, if the load was concentric, then there would have been no movement in the column. But because the load is eccentric here, it's acting from one side, then the moments come. Now the moment M is acting at the top of the column here, for this column, for example, this column I'm talking about. So that moment we can say is, or we can say that the load P is equal to moment by E, where E is the eccentricity. Now, where does that come from? For example, it's a uniaxial eccentricity on this column, and it's at a distance of Ex towards the X direction. This distance from here till here is the eccentricity, and that is Ex. So the actual load that was acting on the cross section of this column was P. Now that load is getting transferred into moments. So movement is always a lever arm. It acts as a load into the lever arm. So this is the load and this is the lever arm. So that will be the movement that will be generated about the cross section. Movement into lever arm, it will be generated at the end, at the center of this section. So the movement that's generated through the cross section, through the center of this cross section, due to the eccentric loads, is the P load, which is acting perpendicular here. it's acting perpendicular like this into the frame, and then there is a lever arm E perpendicular to that. So there is a moment which is generated about the cross section, the center of the cross section. So that moment is M, or you can say mx in this case if you're taking it about x direction. So this would be about mx would be p into ex. Because the loads were unsymmetrical, as well as the beam is acting unsymmetrically onto the column, then you are getting eccentricity ex, and from that you are getting the moments. Now that moment m at the top here would be the maximum moment that generated at the top. So this moment mx is actually what you are getting as the maximum moment, but the same amount of moment will be transferred. The same amount of moment will be transferred to the bottom of this section, or it could be less than that. The amount of moment transferred to the bottom of the section could be equal or less than that. Now it depends upon the amount of rigidity of this support here. So whatever the moments that you are actually applying at the top of the column here, how are you applying that? You're not applying the moments. The load is coming from the beam, which is unsymmetrically placed, and that's transferring the load eccentrically onto the column. That's generating moment m here at the top, or mx, and then there is a reaction at the bottom of the at the support to this moment, which is transferred. Now that could be m or less than m, depending upon the rigidity or the fixity of this support here. Now, if it's a hinge support, then you may probably not be getting the movements at the bottom. What you are getting then is the lateral movements in the hinge support. ये movement पे transfer हो जाता है towards lateral translations in a hinge support. In a fixed support, you are getting a reaction in form of a moment. So now if you realize what would be the behavior under uniaxial, this is what we are focusing on. How do columns behave under uniaxial loads? तो कैसे behave कर रहे हैं? Now this column is under a complex loading sequence. You can take this M1 and you can take this M2, for example, if they are not similar, and you have a fixed support, for example, or any support at the bottom. Apart from this moment that's acting on the column, you still have then concentrically placed payload, which will still keep on acting. Movements are generated due to eccentricity of the payload, but then वो तो movements निकल गए उससे, जो eccentricity portion था that generates movement. Then you can transfer the जो payload है towards the center of this column. You can then transfer it towards the center of this column because you have taken into account the eccentricity. ये लोड एक्चुअली में एक्ट यहां पर कर रहा था, was acting somewhere here, but you have taken into account the eccentricity portion, और उससे moments आपने निकाल दिया जितने आ रहे हैं, then this P load is shifted towards the center. Now this column is under two loads now. Load P actually acting and moments M acting along the cross section of the column. So there are two loads acting on this column, P and M. Now, for all columns, there is a combination of PM loads, and the interaction between them is known as PM interaction. And we accordingly plot the PM interaction curves for each column. We plot P to M interaction curves for each column. And these curves usually act like this. They are somewhat like this. Now this is P, this is M. If the load is 0, the moments are 0. This is 0, 0. So you will have many PM interaction curves for each column. Depending upon the eccentricity of the load that's acting on the column. You can have many PM interaction curves. Now, when the load is increasing P at a designated eccentricity, for example, with increase in eccentricity, this is increase in eccentricity, you are getting more moments. So, for example, if this is E1, this is a curve for E1, this is curve for E2, E is eccentricity, E3, this is curve for E4. Here, E1 is greater than E2, is greater than E3, is greater than E4. From these curves, you can get, for example, there is a load of this much magnitude acting at eccentricity of E. You can accordingly get the amount of moment from these curves. And these curves are available from these are known as SP, and SP16 is the design explanation or commentary or guide, you can say, for IS 456. And SP16 you can use for design of the columns. SP16 is also available to you. It's just they are used for explaining in a much, or you can also get various charts from SP16 or the commentary of IS 456. And these charts are available in SP16. So this was about the behavior. How do the columns behave? Now, in biaxial eccentricity, there will be two types of moments acting on this. There are two types of moments acting in biaxial eccentricity. For example, the load is passing through somewhere here. Now the answer to that question was it was passing through in the first quadrant somewhere here. It will pass somewhere in the center of this. It's passing through this point. What is the eccentric point? जहां पर आपका लोड का सेंटर होगा. अब जहां से ज्यादा बीम्स की लेंथ है या ज्यादा लोड है, obviously the center of the load transfer would shift towards that side. Now this is under biaxial eccentricity. So there is Ex on this axis, along this is Ex, then you have Ey along this axis. So from this point to this point is Ey, from this point to this point is Ex. Now the column would be under two types of movements. Then this column, M1 moment would be generated about M1x moment would be generated about y-axis then, and M2 would be generated not M2, sorry, this is M1y. Now about y-axis, sorry, about x-axis, then you get M1y. I'm telling you that this is along, not about, along M1y and about x-axis. M1y and about, and along M1x you have, along x-axis you have M1x and about on y-axis. So there are two types of moments here. Now if I frame this column section, then there will be one moment like this, this is M1x, and then you would have corresponding M2x here, and the other one would be in the other plane, somewhat like this. It's perpendicular. Now it's difficult to draw, it's perpendicular. So this would be M1y. This is perpendicular to it in the other direction. And similarly, you would have M2y at the bottom of this. So there will be two interaction curves for this column. This was PM. PM was here M1. In this case, there is M1x and M1y. So there are two types of interactions. So the PM interaction curve in this case, when you have a biaxial eccentricity acting in two directions, it's not a curve because it's through the interaction of two different planes, one in this direction and other in this direction. So you have movements in two different directions. In that case, what happens is that I'll try to it becomes like a sphere. There are this is about m1 mx, and that's about my. So, or you can say m1y and mmx. So because you have about this axis as well, then it becomes a spherical body. Now this whole is like a spherical, this whole becomes a spherical body. So it's something like this, revolving around like this. When you have two axes, and this axis is P, the load. So for a biaxial eccentricity, you will get, it's known as a convoluted sphere. Now, convoluted sphere. Now, this is a PM interaction sphere. It's a 3D body that you are getting when you have a biaxial eccentricity. Now, how much is the eccentricity? This is the question. How much eccentricity does the column need to achieve? Sorry, not achieve, maximum. How much is the maximum? I would say, I'll put it like, how is the maximum eccentricity that the column can take? Now, if you have eccentricity, such large eccentricity that this becomes, for example, in the uniaxial eccentricity, its eccentric loads are acting somewhere near here at the end of the column. Now, those loads will not be transferred properly through the column. Why? Because column has itself got a ring, and then the load transferring mechanism is through stirrups, through longitudinal bars, which are placed through the length of the column. जो भी load आता है, they are being resisted by the longitudinal bars. Now, if the eccentric load is such large that it's outside this boundary, then those loads will not be transferred through the column. Thereby, large amount of eccentricity is not good for a column. So you have to maintain a balance while designing, that the eccentricity does not cross a maximum eccentricity. It should not cross the maximum eccentricity. Now, what specifies the maximum eccentricity? Similarly, codes then mention minimum eccentricity as well, that you have to take while designing. Now, why is that needed while designing? Why is the minimum eccentricity? You would say minimum eccentricity for a concentric column could be 0. Now, why do we still need a minimum eccentricity? Its value greater than 0 given in the code, not 0. even when it's concentrically loaded, the value still is given by the code greater than 0. First of all, maximum eccentricity, you don't have a defined thing, but your maximum eccentricity should not be greater than 1/4 of the section, or otherwise your section will not behave properly. It should not be greater than 1/4, 1/4 of the section. Minimum eccentricity is given with the code. Let me show you this. This one. It's given in the code that you have to maintain a minimum eccentricity. All members in compression shall be designed for minimum eccentricity. This is page 70. In accordance with 25.4, where calculated eccentricity is larger, the minimum eccentricity should be ignored. Now, minimum eccentricity is given in 25.4. Just a minute. This is here, page number 42. Minimum eccentricity. All columns shall be designed for minimum eccentricity equal to the unsupported length of the column by 500 plus lateral dimension by 330, subjected to minimum of 20, where biaxial bending is considered is sufficient to ensure that the eccentricity exceeds the minimum about one axis at a time. So the code mentions that you provide eccentricity at least equal to E minimum is at least equal to L by 500, L by 500 plus D by 50, sorry 30, D by 30, or now here L is the, right now it's telling you unsupported length. I will explain that to you. Yes, I'll be finishing in 5 minutes. Unsupported length, and then you have D, lateral dimension of the column. D is the lateral dimension of the column. So your minimum eccentricity depends upon L, it's the unsupported length, and D is the lateral dimension of the column. But it should be greater than 20 mm. Okay. So I'll be stopping right now. So in the afternoon we can take further class, but I think after 3.